We're not going to do one for every single atom. That's going to be tedious. So the scientists sort of stop there. Okay. So in a second, I'm going to show you how these things become a little bit more streamlined. The unifying way of looking at this whole stuff. There is one way we can describe atoms and molecules, and that works. So well, after this slide, I think, after the example from the slide, we'll get there. Okay, de Broglie, which a French scientist, posited that electrons can also act as waves. Basically said, well, Einstein said that light can act as particles, even though we think of it as a wave. Well, can we look at it the other way? Can stuff like matter act like a wave? And the answer is yes, it can. And it involves this equation, the Broglie equation. So I can calculate the wavelength of U if you wanted to. You just have to put in your mass and your frequency and your h, and you're going to get your wavelength. That's, you know, so if I measured the light that's emitted from you, I can tell you what's your wavelength, you know. And we'll look at an example, you know, like actually right now. So calculate the wavelength. I want to know the wavelength in meters, okay, of a wave emitted from a 1 kilogram mass moving at 1 kilometer per hour. Okay, so let's look at this example here. So I misspoke. This thing is not new. This is V for velocity. So I'm going to look at this here. This is V for velocity. So to get this, I have wavelength is equal to h over m times v. This thing is V for velocity, speed. So I gave you V. I gave you mass. Okay, you know h, you can calculate the wavelength. The only thing you have to make sure is everything is in SI units. SI for velocity should be meters per second. Okay, I have kilometers per hour, so I have to just convert that to meters per second. So 1.00 kilometer per hour. I need that in meters per second. So just dimensional analysis. I'm trying to get rid of hours. 1 hour is 3,600 seconds. So I can make this into seconds. And kilometers, I want to get that into meters. And I know that I have 1,000 meters per kilometer. And therefore, 1 kilometer per hour is actually 0.278 meters per second. Isn't that funny to think about? 1 kilometer per hour, which is, you know, a slow walker, is basically 0.278 meters per second. So anyway, that I can throw that in here as the velocity. Mass in SI units is kilograms. Great, I give it to you in kilograms. And h is a constant. So the wavelength of this 1 kilogram thing, okay, 1 kilogram weight or whatever it is, something that's moving around, something you can hold. A kilogram is something you can envision. You can buy that in the stores, like maybe an apple could be a kilogram, something like that, right? And it's like 2 pounds, something that's 2 pounds about. So a 2 pound apple is huge. So this would be 6.626 times 10 to the minus 34th joules seconds, that's h, divided by the mass, which is 1.00 kilograms, and the velocity, which is 0.278 meters per second. Everything here is in SI units, so everything is kosher. I can throw all this together, and I get that the wavelength, if you do this, is going to be 2.38 times 10 to the minus 33 meters, meaning that if I'm looking at the wavelength of this ginormous apple that probably doesn't exist, the distance between the peaks is something like 0.00. something to this effect. This is the distance between the two peaks. So pretty useless. Not going to be anything that you're going to actually see. So that means that yes, you and I are waves, but our wavelength is so small that we're pretty much not. We can't detect it. Our frame per second for our eyes and for our universe is so not in tune with the waviness of ours. So don't worry about it. But it is something that is technically applicable to all matter. But if you apply it to an electron or something, then you're going to get something that's a little bit more useful. All right. As a matter of fact, if you calculate the wavelength of an electron, you would get something of in the nanometer range or so. Just so you know, a fraction of a nanometer. All right. So that's it for this quantum physics-y stuff. Well, actually, there's the Heisenberg uncertainty principle. That's something that there is an equation associated with it, but I'm not going to bother with it because you can't actually apply it for in our class, so we won't. So, but basically, all of this says is Heisenberg posited that he's another World War II scientist. He posited that if you want to find out where an electron is in an atom, or if you want to study an electron in an atom, you can tell either it's how fast it's going or where it is. You can't tell both. Okay, that's the crux of the Heisenberg uncertainty principle. Okay, if I try to find out where it is, right, in the atom, my detection, the way I detect it, is going to change its speed. So yes, I can find out where it is, but as soon as I do that, it's going to change its speed. Okay, and conversely, if I want to calculate how fast it's going to change where it is. So I can't do both simultaneously. That's not going to happen. So, and he proved that statistically, and it's not just limited to how we perceive the world. It is sort of like a principle that can actually be broken. We're always going to have that uncertainty built in. We can't get both at the same time, which is problematic if you want to actually study this stuff. So it's a very qualitative principle for us in this class. If you take quantum mechanics or quantum chemistry or quantum physics, you will learn this probably to a higher